Welcome to the session on distributed data management of the lecture NoSQL databases. The lecture is based on the book Advanced Data Management, where you can find more information. In this session, we will cover several aspects of distributed databases. The reason why we need distributed databases is scalability. There are two options to enable scalability. On the one hand, scaling up, also called vertical scalability, means that you add more power to a single database server. On the other hand, scaling out, also called horizontal scalability, means that you add more servers to a network of computers. In the case of scaling out, a distributed database hence corresponds to a collection of logically related data that are, however, physically distributed over a computer network. A distributed database management system manages these distributed data and makes the distribution transparent, that is, invisible to the accessing users. Distribution transparency hence ensures that the user is unaware of internal data storage or query processing in a distributed database management system. Distribution transparency covers several aspects. First of all, access transparency means that the user can access the database system without knowing the network structure or the storage organization. Location transparency means that data distribution is hidden from the user in the sense that the user need not know the exact location of a data item he is accessing. Replication transparency means that the user can access any copy of a data item that the system might hold for backup reasons. Fragmentation transparency means that the system internally handles data in a fragmented or sharded fashion. However, the user can access the data as if they were unfragmented, and that he can even combine data from different fragments. Migration transparency means that internal data reorganizations have no effect on how a user accesses the data. Concurrency transparency means that operations of multiple users on the same dataset do not interfere. Failure transparency means that the system is failure tolerant and it can continue processing user requests even in case of failures. We will now have a closer look at potential failures in distributed systems. One failure case is that the server crashes. It might restart after some time, but it might also crash entirely. The second case is failure of a communication link. In this case, two servers connected by the link are no longer able to communicate directly. Hence, their communication has to be rerouted via some other components. The third case is a network partition. A partitioned network consists of two or more subsystems that only can communicate among themselves, but not between each other. A subsystem of a partitioned network may also consist of just a single node. That is why network partitioning and server failures are in general indistinguishable. In a distributed system where failures can occur, failure-tolerant protocols are needed. In distributed systems, propagation of information might be difficult. Messages might be lost so that they don't reach their destination. There might also be a high churn, that is, we have changes in the network due to insertions or removals of servers. Peer-to-peer protocols are algorithms that treat all servers in the network equally. Epidemic protocols are peer-to-peer protocols that spread information in a network like an infection or like gossip. Each server in the network can be in one of three states. If a server is infected, it has received a new message and it wants to pass the message on to other servers. If a server is susceptible, it has not yet received the new message. If a server is removed, it has already received the message but will not pass it on. Several variants of epidemic protocols exist. A simple epidemic is anti-entropy. With anti-entropy, we can, for example, propagate new updates periodically. With anti-entropy, there are no removed servers. Servers will not stop being infective. That is, the infection process does not degrade, neither over time nor due to some probabilistic decision. In contrast, a complex epidemic is rumor spreading. That is, an infected server can send several messages over several rounds, but after some time becomes removed. This is why the amount of infections decreases with every round. This decrease can, for example, be triggered by a probabilistic decision. For example, after sending a message, a server can decide in one out of k cases to become removed. Alternatively, the server can also maintain a counter. After sending a message k times, it will turn into a removed server. When using Epidemic protocols, servers have to compare their message lists. By using so-called hash trees, a quick detection of identical message lists is possible. First of all, each individual message is hashed by using a hash function. Then the two hash values of two neighboring messages are concatenated, and this concatenation is hashed again. This concatenation of hashes and rehashing is repeated. In the end, we reach a top hash that covers all hashes of all included messages. If the two top hashes of two servers are identical, we can be sure that their message lists are also identical. For this process to work, all servers need the same sorting order in their message lists, and they have to apply the same hash function. If the two top hashes differ, we can also compare internal hash values and quickly detect different subtrees and hence different subsets of messages. The advantage of hash trees is hence that instead of comparing the two message lists of two servers sequentially, we can now look up in the tree and identify those messages on which the two servers differ more efficiently. The next topic is fragmentation. Fragmentation or sharding splits data into distribution units called fragments or shards. Fragmentation has several advantages. For one, data locality can be improved by putting data into the same fragment when they are often accessed together. When ensuring data locality, we can also minimize communication costs because queries can be answered ideally by just accessing one fragment. Query performance as well as index maintenance can also be better on smaller fragments instead of the entire large dataset. And last but not least, by maintaining several small fragments, we can balance the storage capacities and the workload in the network of servers. However, some disadvantages go along with fragmentation. For example, queries that combine data from different fragments are costly to compute. Moreover, backup and recovery are more difficult in distributed systems as opposed to a single server system. The next issue we want to address is allocation, which answers the question how data could be best distributed in a network of servers. In particular, this means that we want to decide which data items should be stored on which servers. With a good data allocation, we can also handle load balancing in the network. A general distinction can be made between range-based, cost-based or hash-based allocation. With range-based allocation, each server is responsible for a range of values, for example, the range of values for the row key or the document identifiers and the like. With the cost-based allocation, each fragment has an assigned cost, for example, the storage size or the expected query workload. With hash-based allocation, the document identifiers or the primary keys are hashed and based on the hash are assigned to some server. Recall that a hash function maps an input to a smaller output. In particular, a good hash function should spread the input values uniformly among the range of output values. The modulo calculation is a very simple example of a hash function. Consistent hashing is an advanced form of hash-based allocation. With consistent hashing, a hash value for each server is computed, for example based on the server name or the IP address. We also compute a hash value for each data item, for example based on the document ID or the primary key. The idea of consistent hashing is that all hash values form a ring. The servers occupy some position of the ring depending on their hash value. When new data items or files have to be stored, they are based on their hash value allocated to the next server with the next highest hash value in clockwise direction on the ring. When a server leaves the network, the files allocated to this server are relayed to the next server on the ring. When a server is inserted in the network, the files with lower hash values are allocated to it. Consistent hashing supports a heterogeneous network of servers. That is, some servers might be more powerful than other servers. For these servers, we can create virtual copies that have their own server ID and hence their own hash value. In this way, more data items are assigned to the more powerful servers. The next topic is data replication. Data replication means that several copies of a data record are stored at different database servers for backup reasons. The copies of a data record are also called replicas, and the number of servers on which the copies are stored is called the replication factor. Advantages of replication include higher reliability and higher data availability. For example, if a server crashes, the copies can still be accessed. In addition, we can also achieve lower latency in terms of better load balancing of queries between the copies, better data locality when a client accesses one copy, and parallelization by using different copies for different users. Disadvantages of a replication include that consistency problems can occur. For example, updates made at one replica have to be propagated to all other replicas. Moreover, if multiple users write to the system, we can also have concurrency problems because the user's transactions can interfere. Master-slave replication is one form of replication where updates are performed just as at a single master site and all other copies are the slave sites that can only be read. Because the master server is the only site accepting write access, it is also a single point of failure. When replicating multiple data records, a server can act as a master for one data record, but as a slave for another data record. A further distinction can be made between eager and lazy replication. Eager replication tries to immediately update all replicas, whereas lazy replication allows for some delay during the update. A different form of replication is multi-master replication, also called update anywhere. Here, updates are permitted at any server holding a replica, and updates are automatically propagated to all replicas. If now concurrent writes by different clients occur, a resolution of such conflicts is necessary. A multi-master system offers better response time and an increased availability for write accesses because we avoid the bottleneck of a master server. A general question is how many replicas are necessary to achieve a failure-tolerant system. Let us assume we have two replica servers. If we assume that at most one server fails, it can later on restart and synchronize with the second server to receive the newest writes. However, with a replication factor of just 2, the probability is high that the two servers fail at the same time. In this case, the system is unavailable. Hence, it is usually recommended to have a replication factor of at least 3. Two methods to handle temporary failures and outdated copies are hinted handoff and read repair. If a replica server is unavailable, hinted handoff sends a write request to another server that is available but not actually acting as a replication server for the data item. The write request then contains a hint to which server this write request should be relayed as soon as the server starts up again. On the other hand, with read repair, a coordinator node sends out read requests to a set of servers to obtain a majority vote from all replicas. The coordinator hence sends the read request to a set larger than the needed quorum or majority in this case. If the majority of replica servers returns the same value, this is the result sent to the client. However, some replicas might have returned outdated values. To these replica servers, the coordinator sends out repair instructions so that they can synchronize with the other, more up-to-date replicas. A major problem in distributed systems is concurrency control. The two-phase commit protocol is used to finalize a distributed transaction between a set of servers called agents. The servers or agents have to participate in a voting phase and a decision phase. A major problem of the two-phase commit protocol is that failure of a single agent leads to a global abort of the transaction. In the protocol, there's the so-called in doubt state, which is the state between the two phases before the coordinator sends his decision to all agents. If the coordinator fails during this in doubt state, the other agents cannot proceed because they did not receive any decision from this coordinator. Here we see a good successful run of the two-phase commit protocol. In the first phase, the coordinator tells all agents to prepare for the commit. All agents have to respond that they are ready to commit. In the second phase, the coordinator tells all agents to commit. All agents have to acknowledge the commit back to the coordinator. One unsuccessful case of the two-phase commit protocol happens when one agent is not ready to commit. In this case, the coordinator has to send abort messages to all agents that answered with a ready message. The consensus problem addresses the case of a distributed database system with multi-master replication. All servers can send update messages for a data record. If some of these update messages are lost, the system has to agree on the correct final value and the right order of updates. In this case, a consensus algorithm ensures that a single one among the proposed values is chosen. A prominent consensus algorithm is Paxos that keeps a distributed database system in a consistent state under certain failure conditions. A client issues a request to the system. The database servers have to come to a consensus among them on what the current state of the requested record is. In the Paxos protocol, the database servers act as different agents. They can be proposers, leaders, acceptors, or learners. In particular, each database server can act as several agents at the same time. For example, a database server can be both a proposer and a learner. The Paxos algorithm consists of a prepare phase and an accept phase. Among the agents acting as proposers, one is the leader for this round of Paxos. For this round of Paxos, the leader chooses a unique proposal number n that should be greater than any other previous proposal number. Whenever an acceptor receives a prepare request, it checks whether the proposal number is greater than the proposal number of any prepare request it has received previously. If this is the case, it can send a promise request to the leader. It means that it will not accept any proposals numbered less than the current proposal number. The promise response also includes the highest numbered proposal it has accepted, that is, the proposal number as well as the value that was accepted. If the leader receives promise messages from a majority of acceptors, it can start the accept phase. If the promise messages contain proposal numbers of previous rounds, then the one with the highest number is chosen, and the value of this highest numbered proposal is chosen as the accept value. If the promise messages do not contain proposal numbers of previous rounds, because the acceptors didn't send accept messages so far, then the leader can choose a value v for acceptance. If the leader has chosen a value v, it will send an accept request to all acceptors, including the current proposal number and the chosen value v. The acceptors having received an accept request can return an accepted message. However, acceptors will only send an accepted message if they did not respond a promise message to a prepare request that has a greater proposal number than the one received in the accept request. Here we see an optimal run of a Paxos round. The leader receives a request from a client. The leader chooses a proposal number and sends prepare requests to the acceptors. The acceptors return promise messages and also include the value of the highest numbered proposal they have accepted so far, in case they have already sent out accepted messages in previous rounds of this Paxos run. From the values returned in the promise messages, the leader chooses the one with the highest previous proposal number. In case there are no previous proposal numbers, the leader can choose a value freely. In phase 2, the chosen value is sent in accept messages to the acceptors. As a last step, the acceptors return accepted messages, including the proposal number and the value. In our setting here, the acceptors return the accepted messages to special agents called learners. There must be at least one learner available that can return the value to the client. Note that the leader can also act as a learner. Before returning the value to the client, the learner has to check that the majority of acceptors really accepted the value that was chosen by the leader. The Paxos algorithm ensures that a value is chosen with a proposal number n if and only if a majority of acceptors really accepted that value in the second phase with a given proposal number. This is ensured by three properties of the Paxos algorithm. The first property that Paxos relies on is that any proposal number is unique. The second property refers to the majority vote. Requiring a majority of responses ensures that any two sets of acceptors have at least one acceptor in common. This enables the leader to find out which was the highest numbered proposal previously received. Hence, the majority property leads to property 3. The value sent out in phase 2 is the value of the highest numbered proposal of all the responses in phase 1. So far we have only seen a good run of Paxos. However, some agents might fail during the execution. The good thing of Paxos is that a certain number of acceptors might fail. We only have to ensure that a majority of acceptors reach a consensus. More formally, if we have a total number of 2f+1 acceptors, f acceptors may fail, as long as f+1 acceptors still agree on a common value. Learners are those agents that return the chosen value to the client. That is, at least one learner must be available at the end of phase 2. Failures of a leader can also be handled by Paxos. If a proposer notices that the current leader is not responding, it can take over the client request. It will make itself the new leader by restarting phase 1 with a higher proposal number. However, if leaders are only temporarily unavailable, we run into the problem of dueling leaders. In this case, the two competing leaders keep restarting phase 1 with higher proposal numbers. However, the system will never reach an agreement. This is because acceptors receive prepare requests with higher proposal numbers before being able to send out accepted messages for the lower proposal numbers. A workaround for this problem is to include random delays for each leader before he starts phase 1 again. Due to this delay, the second leader might be able to finish phase 2 before the first leader restarts phase 1. We now come to the topic of version vectors. In a multi-master system, the precedence and ordering of updates has to be determined without having a system-wide global time. A vector clock is a vector of counters, and there is a logical counter for each client. In the picture you see 3 clients, A, B and C, that write to the same data item. After each write operation, the counter of the client is increased. However, clients might write to different replicas of the same data item concurrently. During a synchronization step between the replicas, the system has to determine what the correct value is. A simple automatic synchronization operation is union semantics. A good example for union semantics is a shopping cart. If different products are placed into the shopping cart at different replicas, we just combine them into a single shopping cart and union the contents at the end. Another option for version vectors is using sibling semantics. In this case, the system is not able to synchronize two diverging replicas automatically. It keeps the two divergent versions as siblings. A client is required to reconcile the two divergent versions into one, The client has to write the reconciled version to the system and increment the version counter appropriately. It is important to note that we indeed need version vectors with counters for each individual client or accessing application. In particular, it is not sufficient to just keep counters for each replica. For example, if client A and B write to one replica and we only have a counter for the replica, then client B could overwrite all previous writes of client A. In this case, all writes of client A would be lost and not be reflected in the system. As the final topic, we will have a more abstract view on consistency problems. Three general properties of distributed systems are consistency, availability, and partition tolerance. The strongest requirement for consistency is whenever a server modifies a value in one replica, the value must be immediately available in all other replicas. Or at least the value should be updated before any other client accesses it with a read request. Ensuring this strong form of consistency is costly for a large number of replicas. In particular, the system might have to block read access until all replicas are updated, which is of course bad for availability. Availability, on the other hand, means that the system provides high performance for query answering, but also for write requests, and we have a very low response time. However, as we have already seen, failures in distributed systems are common, like for example failures of communication links or servers, as well as network partitions. Partition tolerance of a distributed system ensures that failures of single servers do not lead to failure of the entire system. In particular, in case of a network partition, the partitions are still able to operate independently. The so-called CAP conjecture covers the fact that from the three properties of consistency, availability, and partition tolerance, not all three can be achieved at the same time. In distributed systems, failures can usually not be avoided, and certain systems require high availability, like online shopping. Such systems are often called AP systems because they prefer availability and partition tolerance and disregard consistency. Strong consistency is really hard to achieve in a distributed system, in particular in terms of availability of the system. As already mentioned, if after an update any subsequent access returns the updated value, read accesses must be blocked, which reduces the availability of the system. Hence, to improve availability, it might be worthwhile to consider more weaker notions of consistency. That is, after an update, a client accessing the data item might not be able to see the most recent value. The period of time between an update and the point of time when all accesses return the updated value is called the inconsistency window. So-called eventual consistency is a specific form of weak consistency. It says that if no new updates are made, eventually, that is after the inconsistency window has passed, all accesses will return the last updated value. To ensure strong consistency, some distributed systems use write and read quorums. The read quorum is the subset of replicas that are contacted when accessing some data with a read request. For a successful read, all of these replicas in the read quorum have to return the same value. Similarly, there is a write quorum, a subset of those replicas that are contacted during a write request. For a successful write, all replicas in the write quorum have to acknowledge the write request. Strong consistency can be achieved by two quorum rules. N is the total number of replicas, R the read quorum size, and W the write quorum size. The rule for consistent reads requires that the sum of R and W is larger than N. In other words, the read quorums and write quorums have to overlap. The rule for consistent writes requires that 2 times W is larger than N. In other words, any two write quorums have to overlap. If we relax these rules and allow so-called partial quorums, for example due to failures, we can only ensure weak consistency. Typical quorum systems obeying the strong consistency rules are read one, write all, or majority quorum. In a read one, write all system, there's only one server included in each read quorum. However, the write quorum covers all existing replicas. In a majority quorum system, both the read and the write quorums each have to cover a majority of replicas. This was the last topic of the lecture, and I close with a conclusion. During the lecture, we have seen many data models other than just relational tables. We have seen that there are lots of different query languages and there are basically no standards for the different data models. We have also discussed problems with consistency, in particular the so-called CAP conjecture. When using novel database systems, there might be problems with reliability, for example due to missing long-term experience or the dependence on open source development teams. And lastly, which database or data model you choose really depends on your needs and the needs of the accessing applications. This was the topic on distributed database systems. Thank you for listening.